All right. Uh, so good afternoon, everyone. My name is Mohit Gar, and today I'm going to talk about or like present this paper that I'm sure every one of you would have read in the last week or so. The evaluation of distributed concurrency control. This paper is by Rachel Harding from MIT and other authors from CMU and such. So first, let's look at sort of the motivation and challenge of distributing transactions. So let's say you have a database which holds some records which are distributed over some time frame, let's say months, and you have some transactions which I have characterized or classified here based on the records on the months or the time frame that they access the records for. So as the number of transactions increases, then it puts a lot of pressure on the single node memory and the CPU. So the most natural way to sort of increase your throughput or performance is to basically scale out. So as you scale out, what you can do is partition the data. So there could be one partition on a node which just has records for the month of January, and the other partition could have Feb, and the third partition could have March, and the transactions can just access that partition. So that way we can efficiently distribute the load, pardon me, the transaction load that we are trying to service. So depending upon the amount of resources you want to deploy, theoretically you can have infinite parallelism. However, the problem comes when you have these pesky transactions that want to access more than one partition. So, for example, you have a transaction which wants to access some data from the month of January, and some transactions that want to access the month of Feb. Then you would have these transactions conflicting with the transactions that are just accessing the single month data or a single partition data. This is especially bad if the operations are conflicting. For example, let's say the Jan-Feb transaction is trying to modify some records, and the Feb transaction is essentially trying to read the operations. So in this case, we want some serializability in these transactions. To provide that serializability, we need some form of locking mechanism. And if the system is distributed in nature, if these are shared nothing nodes, then in that case, we would require sorry, some sort of coordination as well. So when the network comes in, then the performance would obviously be affected because of the network bottlenecks. So the question that arises is that is distributing transactions bad, or is it good? So throughout the paper, we'll look at different serialization protocols through the framework that the authors present in this paper, and sort of try to answer this question. So first intuition that the authors provide is that it basically depends. So it depends on what the workload that of the transaction workload looks like. So what's the update rate in the workload? So we can intuitively think that the reads can be easily pipelined, but the writes are the transactions that try to write something to write a new record or update an existing one are the ones that could create problems for which we need the mechanisms that are discussed in the slide before. And the second part is what's sort of the contention characteristics in the workload. So there could be some transactions, workload of transactions that just accessing a single record. Then there could be some workloads in which the transactions are accessing the records that they are accessing have a have a more uniform distribution. So using these workloads, we would want to answer questions like what kind of performance can we achieve, and what kind of scalability can we achieve with this for these workloads, or for the protocols that provide us the serializability. So the protocols in database systems which help us get the serializability can be classified into five major categories. The first are, and the more traditional ones are, the two-phase locking protocols, in which what we do is the transaction tries to acquire locks on the records that is it is trying to access, or either read or update. Then the second category is the timestamp based protocols, where the transactions are serialized based on the timestamps that are allotted to those transactions. Then another category is multi-version concurrency control, which is where you basically maintain several snapshots of the data records. So later, a read transaction can be like, okay, this is like or a write transaction can be like, hey, this one is a older version, so probably I should wait if some other transaction is in progress to touch this piece of data. We'll look at some of these protocols in a bit deeper manner in the upcoming slides. So another category is the optimistic concurrency control, and optimistic concurrency control, what it tries to do is it tries to delay the resolving of conflicts as late as possible. So we only look at conflicts when just before committing a transaction. And finally, you have these deterministic methods, which take the exact opposite approach to OCC methods, where they try to prevent conflicts from the get-go. So just before a transaction is started, it tries to solve the conflicts. So the problem that the authors try to raise in this paper is that in a lot of they do a study of recent publication and look at what the protocol that the publication presented was compared against. So as we can see from the table, only 6 out of the given papers compared against two-phase locking. 7 of them didn't compare against anything. Only 3 compared against OCC, and only 1 compared against the deterministic methods, protocols which follow the deterministic method technique. The last one is more understandable because this technique is more recent, but the rest of the lack of comparisons is really unfortunate to see. So that's sort of the problem that this paper tries to solve. So the authors provide a new framework called Deviva, which compares all these, which aims to compare all of protocols through all of these variety of techniques. So it in their words, it tries to provide an apples to apple comparison of this protocol. So let's now just quickly look through, just briefly look through all of these protocols, so that we can have a better idea when we sort of look at the evaluation of these protocols using Deviva. Oh, so first actually look at the framework Deviva itself. So the framework is they try to keep it as simple as possible. So you have a lot of client processes, and then you have server processes, and these are basically, they don't share anything. They are hosted on different instances, and they have also kept the database in memory. So that is to not have any overhead from writing to disk and stuff like that. And that is basically the theme of a lot of reasons that they have taken in the design of Deviva, that they don't want any overhead or any interference from unrelated components. So that interference is the aim to provide to not have interference from other components is basically why they created their own database management system, where they have just not implemented or tried to like avoid the other components as much as possible. And they also haven't provided any replication or fault tolerance, which can be looked as a limitation or as a feature depending on what you are trying to derive from the experiments. Then the servers are allotted requests using consistent hashing, and each server basically has a single partition. There could be multiple partitions per server, however. So let's dive a bit deeper into Deviva. So you have this server. So all of these transactions are essentially stored as stored procedures. This is done so as to avoid any overhead from SQL parser, planner, optimizer, etc. So once this procedure is stored at the server, now the clients uh, can execute transactions depending upon the workloads. They can have stored procedure parameters that are passed to the server. So this server would now just have a mix of read or update operations. So the inside the server we have the standard, there are request threads that try to add the request to a priority queue. Now the interesting part here is the multi-core execution engine, where uh, it has 4 worker threads which read requests from the priority queue and execute it. So they also have an access to a auxiliary protocol data store, where they store data, like for example in the case of lock-based protocols it will store the lock tables. In case of OCC it will store the verification metadata that's required, and it also has an access to the in-memory data storage. So this is the main data store, and this main data store is organized as a simple uh, uh, per partition hash table. In the case of multi-partition transactions, the multi-core execution engine sends requests to other servers. So the format of the request is similar as the client. So it also generates and passes these stored procedure parameters. Also, in case the protocol that's implemented in this engine, if it sends a abort message, then that abort message is also forwarded to other servers that contain the partitions that are accessed by the aborted transaction. And they also provide a mechanism to have an exponential backoff, so the transactions just do not the aborting transactions do not just saturate the system in case there is an abort. And some of the protocols like timestamp and MVCC, these protocols require timestamps. So Deviva also provides that. Uh, it it guarantees a unique timestamp by combining server ID and client ID with the local server time. And Deviva also takes care of keeping the local clocks on the server synchronized. So with that, now let's sort of look at a brief overview of all of the protocols that are implemented in Deviva. So first is the traditional and most widely sort of implemented protocol called two-phase locking. So the two-phase locking is fairly straightforward. It has 2 phases. In the first phase, which is called the growing phase, the transaction tries to acquire locks on all of the records that it is trying to access. So in this phase, there is no release. So only locks are required. In the next phase, that is when the transaction starts releasing the lock. So once a transaction releases one lock, it automatically enters the shrink phase, and at this point, it can no longer acquire any new locks. So uh, it also categorizes these locks. So shared locks are the locks that are required if you want to read the if you just want to read a record, and all shared locks are essentially considered compatible with each other. This will be make sense as we look at one of the protocols under two-phase locking. And the exclusive locks are required when we try to do any combination of updates and reads in a transaction. And the exclusive locks are essentially considered incompatible uh, with uh, with all the other locks, so shared logs or other exclusive locks. So the biggest sort of drawback of two-phase locking is that it can easily deadlock, and all of the two-phase locking protocols are characterized based on how they solve how they resolve this deadlock. So the authors focus on only two protocols for two-phase locking, which they call first is the no-wait protocol. So incompatible lock requests aborts a transaction. So if the transaction uh, is trying to get an exclusive lock on some transaction, if it has a shared lock on a given record, then in that case that transaction would basically be aborted. Then it then another protocol, what it does is, instead of aborting the transactions, if the timestamp is older or the timestamp is lower, then those requests are basically queued. They are not aborted immediately. And the queued transactions can jump the line if they find that some transaction is just holding shared locks for a given record, and it can basically add itself to the parent table for the locks of that transaction. So the next technique for providing serializability is basically called timestamp ordering. In timestamp ordering, the transactions are assigned monotonically increasing timestamps to establish the order of the transaction. So a simple protocol is called timestamp, and that protocol essentially aborts transactions with a smaller timestamp. If some transaction has an exclusive hold on a particular record. So this is pretty straightforward. In Unlike the previous wait die protocol, the transactions are not allowed to are not allowed to jump queue in any case. So when the transaction is aborted, then when it restarts, it gets a new lock. So there's sort of this uh, continuous allotment of higher timestamps, and if the timestamp is older, those transactions get aborted, and so on. And the other protocol that's also classified under timestamp ordering and is compared in this paper is the MVCC, where you have MVCC is multi-version concurrency control. So you have timestamp copies of the records. So the reads access older copies if the writes are not committed, and transactions abort. So as the records are uh, as there are multiple copies of the record, at some point those copies have to be garbage collected. So if the transaction is trying to access those garbage collected record, it aborts and it restarts. And the next technique is the optimistic concurrency control. So as compared to the timestamp ordering protocols, this protocol tries to uh, delay resolving conflicts as long as it can. So it performs arbitration just before it's about to commit. So uh, it 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 moves in essentially three phases. The first phase is you have a read phase. So the per record metadata that the transaction is trying to access that metadata is copied into a private workspace which is served as a reference for later. So there is a validation phase at a later point where the uh, so I missed one point here, that in optimistic concurrency control, the timestamps are not allotted to the transactions before when they start. It's allotted at a later phase. So that later phase is the last phase, and in read phase you are just copying over the metadata for a particular record, as compared to in previous cases you are directly modifying that record metadata. So as you basically in read phase, as you try to like run operations, as you are executing, if you modify the transaction, you set the timestamp in your reference, in your copied reference to infinity. So that is basically to say that, hey, a particular transaction modified that data. So that modified data can then, in the validation phase, we can look at all the transactions, the read and write operations that they did, and resolve conflicts at that point. So this is fairly protocol specific, but the whole idea is that in validation phase, you will resolve these conflicts and try to establish some order between the transactions. So in the write phase, once you have resolved all of the conflicts, the timestamp is allocated to the transaction, and this is the timestamp that is actually written in the database. So any further transactions would do the same thing. Now copy this reference data and go on like that. So although there are several variations for the protocol that the authors implement in Deviva is called MAAT, and it's a protocol by Mahmood et al. It is referenced in the paper. So the last one is deterministic, which is exact opposite of OCC, is where you try to look at the read-write sets for the transactions before you do anything. So before you even start a transaction, you run a reconnaissance phase in which you try to map the transactions to the partition and try to establish an order in which the transactions would be executed. So the uh, the layer that tries to establish order between the transactions is called the sequencer layer, which orders and assigns IDs to a batch of transactions. So the batch is uh, the batches are created in 5 millisecond epochs, and this batch of transactions is forwarded to a scheduler, which is running on the server process. So the server process will talk to a given sequencer, get all the transactions, and assign all the locks that the transaction has to acquire. So the transactions basically run one after another. So after that, in this case, the read-only transactions just do local reads, and they don't require any communication between the servers itself. It just require a communication between sequencers, which form a part of the coordination layer, and the actual servers which maintain the partition. So now, kind of going through that summary, now we can look at the evaluation. So it's pretty standard. They set up AWS instances for clients and servers. So they have 8 CPUs uh, and have chosen a setup where they have very high network performance. So the round trip timing is 1 millisecond. They have 10,000 clients which always keep sending requests. So the way they do the measurement is they do a 60-second warm up in which the clients are sending the requests, and in the next 60 seconds, that is when they measure the throughput of the committed transactions. So the workloads that they have used they have used 3 workloads. The first one is the Yahoo cloud serving benchmark, which is a single table which is partitioned based on the primary key. It has 10 columns. Each columns has 100 bytes char value, and each transaction is limited to a total of 10 records. Another benchmark that they use is the TPCC benchmark, which is pretty standard. So they have only implemented two kind of transactions. First is the payment transactions. The only thing that we have to know about this is that it touches at most two partitions, only with 15% probability, and the new order transaction, only 10% of transactions are multi-partition. So if we run this workload, most of the work, approximately 90% of the work would be local. Only 10% of the transactions would be multi-partition. Finally, to have a, a bit of like, if you want to benchmark any foreign key operations, they have picked up the product part supplier workload, where you have a mix of single and multi-partition transactions, where there are two tables which are like product. There are three tables, and then you have two tables which basically provide a mapping using foreign keys from products to parts, and suppliers to parts. So all of this, there is fairly dense evaluation. The only evaluation that I've included in the slides is just for the YCSB benchmark, but just wanted to show these two workloads, TPCC and PPS workloads, for discussion later. So first, let's look at the so YCSB benchmark is used here. On the y-axis, you see system throughput, and on the x-axis, you see the skew factor. So skew factor is essentially it is a feature of the distribution that they have used for the transactions. So as the skew is increased, more and more transactions access the same records. If the skew factor is lower, there is more uniform distribution of the records that the transactions are trying to touch. So as you see, if the skew factor is less than 0.5, then all of the protocols provide almost a similar performance, except for Kelvin. After 0.5, the protocols basically the performance degrades a lot, and around 0.8, it basically converges to sort of like there is almost zero throughput. So when the skew factor is less than 0.5, Kelvin suffers from bottlenecks in the scheduling layer, so its throughput is slightly lower. But as the skew factor increases beyond 0.5, the Kelvin maintains the performance. It is because in the reconnaissance phase that happened earlier, it has already calculated the result. So the transactions are moving in, have an already established order in between them, and the locks that it requires are, and the locks that that a transaction acquires are not contended by anything else. So in fact,
Mohit, can I ask a quick question?
Yes.
Why is OCC also like Kelvin? It's also not as good throughput as the other protocols. It's similar to Kelvin. Do you have some guesses as to why it's not up there with the other protocols?
Yeah, in the slide for scalability, we will see that while the scheduling layer is a bottleneck in Kelvin, the verification phase is a bottleneck in OCC as well. So the verification where we actually resolve the conflicts is actually a huge bottleneck for OCC protocol.
Okay.
Yeah. In that, I have extracted that graph from the paper where they say that, hey, this is the amount of time that's spent in verification. So there we would see that it forms a bottleneck. So continuing in the update, when the update rate is verified, so the number of transactions have 10 read operations in the beginning, and as we move towards right, the operations become almost 100% update. So you all of the transactions have are update transactions. As we infuse as we input more update transactions, the throughput falls drastically for lock based and timestamp based protocols. So except for Kelvin, everything else, performance of all of the protocol degrades, because for lock-based protocols, as the transactions try to access any exclusive locks, they get aborted. So a similar thing happens with the transactions that are ordered by timestamps. They also start getting aborted. And an interesting point to see here is that the wait die, where you actually don't abort the transaction immediately, falls way more drastically than no wait, which is sort of to be expected because no wait is more aggressive. It aborts the transaction immediately, so it is possible that the transaction can come back and try again. But in wait die, it just hangs out in the priority queue, and essentially no work is being done here. So that time is wasted. So Kelvin Kelvin sort of maintains its performance here as well due to similar reasons. That once in the reconnaissance phase, it's the the locks that the transaction is going to acquire are known beforehand. The transaction goes in, when it starts, it acquires the locks, and it gets executed, and it immediately releases the locks. Since it's not contending with anyone else, the performance is maintained. In fact, it may even be slightly better because now you are not doing the expensive reconnaissance phase in this case. So this one is the more interesting, I guess, the most interesting diagram in the paper, where you basically have on the top you have three figures where the authors have increased the number of servers. On the x-axis, they have maintained they also the graphs. The graph A on the top is with very low contention or no contention at all. So it's like only read-only transactions. In the second chart, it's medium contention. So they have set the skew to, I believe, 0.6, and they have varied the number of servers. And in the graph C, they have a mix of read-write transactions with a skew of 0.7, and this is considered a high contention case. So let's look at the first chart on the top. We see that the timestamp and the lock-based mechanisms um, perform have the highest performance. So in this case, the reads are basically, since the transactions, all they are trying to do is read the records. In this case, the shared locks that are acquired by those transactions can be shared with all of the other transactions. So the reads are essentially pipelined pretty well, and the throughput is it results in a high throughput. Now, in the case of OCC protocols, we can see that the validation phase, that's what Murat was asking. As we can see that on the bottom, they have basically divided, they have tried to like dig deeper into where the protocol is spending most of its time. So I'll just quickly go through the various categories that they have allotted. So useful work is the time the execution engine is actually executing the transactions. The transaction manager is the time where the protocol is updating the transaction metadata and cleaning up the committed transactions. In CC manager, that's when it's trying to acquire locks or like validating, actually doing the validation, and and also like in case of Kelvin, it's doing the it's a time spent by sequencer and scheduler. Two PCs, I didn't mention this, but in Deviva, all of these protocols except for Kelvin are using the two-phase commit protocol, uh, because the system is distributed. So in the abort time is the time where the protocol spends cleaning up the aborted transaction. Idle time is where the protocol is just sitting around doing nothing. So this is the time where you have all of these transactions queued up for the timestamp based and lock based protocols specifically. So uh, uh, coming back to the graph A, we see that the OCC protocol, the verification phase where you are actually doing the verification, copying over data, that forms a bottleneck. That's why the performance suffer. And for Kelvin, the again as the server count scales, the sequencer layer, the scheduler and sequencer layer, that forms a bottleneck when there are read operations only. But in the next case, as the skew is 0.6, when there is a fairly good mixture of read and write transactions, we see that Kelvin shows the most increase, or like it provides way better performance uh, uh, as the it provides way better performance because the benefit of uh, uh, the benefit of rights having rights, it's like better handled in Kelvin as compared to the other. I mean, it's not like Kelvin is performing better, it's the rights have basically killed all of the other protocols because now there are a lot of aborted transactions. However, Novate still maintains its performance, and for OCC protocols, at this point, the distributed nature of the workload, as there are more servers which are handling the conflicts, the bottleneck of the verification phase is reduced a bit. In the final case, yeah, also we see that not only there are aborted transactions because I mean, due to the result of aborted transactions, more transactions are being buffered. So the protocol is spending a lot of time. The timestamp and locking protocols are spending a lot of time just having the transactions queued up in the priority queue doing nothing. That affects their performance. So lastly, in the read write phase where there is high contention, we can see that almost all of the protocols don't perform well. Only Kelvin performs well, and it's the same reason as we can see that on the last graph in the bottom. We can see that all of the timestamp and uh, locking based protocols are spending a lot of time just sitting idle, where there are a lot of aborted transactions, they are getting queued up. So as the server count becomes as the servers are increased from 1 to 64, we just see a throughput gain of just 1.5 to 2 times what so that is fairly low than the 64 times increase that we would expect if the performance increased linearly. So that is less than 10%. So only Kelvin maintains good performance. So overall, we can, looking at the scalability chart, we can see that the distributed transaction processing really doesn't scale. It doesn't really work out. To sort of look at the to sort of make the authors have also done an experiment increasing the network speed. This is basically to make their point on the try to dig deeper into what is the biggest contributor to the bad performance. So I mean, intuitively we know from distributed systems that network is that bottleneck. So that is basically proven in this test case. Since all of the protocols are using two-phase commit, their performance degrades rapidly, except for Calvin, which again maintains its performance. Uh, yeah, so the solutions that the authors propose are first is that you break the speed of light, which is something that you actually cannot do. So so authors suggest that you use some specialized hardware for your network, which can provide you better latencies. So some work has been done on using RDMA and the associated ROC protocol to get better network latencies. So if the network latencies fall drastically, then in that case we would get automatic gains from all of these protocols, which suffer from having the transactions distributed, having multi-partition transactions. Then the second solution that the authors authors suggest is that you partition the data more efficiently. So there are some applications which are easily partitioned. So it would be so all of the analysis, all of the performance degradations that we have seen in the evaluation, these applications are not affected by them at all. So they get this nice parallelism. To sort of emulate those applications, we can look at static and dynamic partitioning strategies for the applications that don't have this natural which don't have this like easily partitionable nature. Uh, then final suggestion that they make is that hey, can we just look at a different programming model? So I mean, they basically say that they basically suggest that a semantic based serializability could be explored, which is basically, as we have seen in distributed systems, we have all of these protocols that try to use the commutativity of commands to get a sort of higher parallelizability and performance. Can we do something similar for serializability protocols? And also, like they have also shown a theory of they have also given an example of these programmers who developed some web frameworks in Ruby on Rails, and how they were uh, able to get sort of define their application consistency in a way that they could achieve really high performance. So the overall idea of giving up serializability is essentially pushing down the application semantics can be pushed down lower into the database, so it can really use some characteristics of the workload itself to get higher performance. And yeah, so the question that we started with was is distributing transactions bad or good? So looking at the results, I have only picked a handful, but there are the paper is fairly dense in terms of experiments and results. So those results suggest that it's not exactly good at this point of time, and but it's still a potential opportunity. We can pick up all of these suggestions, and some of these suggestions have already have a large amount of research behind it. We can look at its implementations and adopting them in practice. So yeah, that's pretty much it. Thank you.